Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. My name is Azmat Ali and I welcome you all in class of Elementary Number Theory by David M. Burton. In last lecture, we discussed about first principle of finite induction. In today's lecture, we will discuss about second principle of finite induction, as well as we discuss what is the relation between mathematical induction, first principle of finite induction, and second principle of finite induction. I have observed that students have much confusion in these three topics. So firstly, we discuss how mathematical induction is related to first and second principle of finite induction. Firstly, recall what you learned in your class 11 about mathematical induction. Why we use mathematical induction. Mathematical induction is actually a method that is used to prove any mathematical statement or formula or a mathematical inequality or proposition, etc. We say suppose Pn is any given mathematical statement. This is my mathematical statement that I have to check for all positive integers. In mathematical induction, the first step is we check the statement for n is equal to 1. If it is okay, then we suppose that the statement is true for n is equal to k, and we check statement for n is equal to k plus 1. If k plus 1 is also true, then we say Pn is true for all positive integers. So this is the definition of mathematical induction. Now, how first principle of finite induction and mathematical induction and second principle of finite inductions are related. Actually, mathematical induction, as I have discussed, this is a method. This is a method to prove a mathematical statement. Either it is true or false. Now, this mathematical induction has actually two subparts or two types. First type is called first principle of finite induction. First principle of finite induction. And the second part is second principle of finite induction. Second principle of finite induction. So I can say first principle of finite induction and second principle of finite induction are itself mathematical inductions, but they have some different conditions. In first principle of finite induction, we say suppose we have given a mathematical statement Pn. Like as in mathematical induction, here also we check statement is true for n is equal to 1. Then we suppose statement is true for n is equal to k. And lastly, we check whether statement is true for n is equal to k plus 1. If these three are okay, then we say statement is true for all positive integers. In other words, I can say that the first principle of induction, finite induction, is actually mathematical induction that you learned in class 11th. So there is no difference here in first principle of mathematical induction, first principle of finite induction and mathematical induction. While the second principle of mathematical induction has some different. In second principle of finite induction, we check is the statement true for n is equal to 1. If yes, then we move towards second condition. Now, in second condition, there is a difference from first principle of finite induction. In second condition here, we say if statement is true for n is equal to k such that statement is true for all preceding integers. Mean to say statement is true for n is equal to 1, statement is true for n is equal to 2, statement is true for n is equal to 3, up to so on. Statement is true for all positive integer up to k. If the statement is true for all these integers, then we check is statement true for n is equal to k plus 1. If now statement is true for n is equal to k plus 1, then we say that the statement is true for all n belong to n. So this is the difference between first principle of finite induction and the second principle of finite induction. In first principle of finite induction, we just assume the statement is true for only n is equal to k, and we check is the statement is true for n is equal to k plus 1. While in the first principle of in the second principle of induction, we suppose statement is true for all the preceding integer, then k plus 1 is true. That is, statement is true for all these integers. Then we check whether the statement true for n is equal to k plus 1. If yes, then we say the statement is true for all positive integers. So I hope now you have a clear understanding about these three concepts. Mathematical induction and first principle of finite induction, these two are same. Second principle of finite induction has some difference in second condition from first principle of finite induction. Actually, first principle of finite induction and second principle of finite induction both are the types of mathematical inductions. The condition that you read about mathematical induction in class 11 is same as the first principle of finite inductions. Now we move towards the proper definition that is given in David M. Burton book. Actually, David M. Burton does not use the word statement or does not use the style like this. Pn is a mathematical statement. He says, suppose S is a subset of natural number. Suppose S is a subset of positive integer that have the following properties. 1 belong to S. 1 belong to S mean this is same as when we say statement is true for n is equal to 1. But here in David M. Burton book, he says 1 belong to S, 1 belong to S mean 1 is an integer of S. If k is an integer such that all the preceding integer 1, 2, 3 up to so on belong to S, this implies k plus 1 is also belong to S. If these three conditions hold, two conditions hold, then we say S is a set of all positive integers, that is S is itself equal to set of positive integers n. First principle of finite induction versus to second principle of finite induction, I have already discussed. In second principle of in the second condition of first principle of finite induction, FPI, we just assume whenever k belong to S, then k plus 1 is also belong to S. While in the second principle of finite induction, SPI, we assume if 1, 2, 3 up to some k, these all integers belong to S, then k plus 1 is also belong to S. In other words, in first principle of finite induction, these are the same line that I have discussed already. So we can say that the condition of the second principle of finite induction are stronger than the first principle of finite induction. That's why second principle of finite induction, sometimes also called stronger induction, and the first principle of finite induction is called weaker induction. How to use second principle of finite induction for numerical problem? This also I have discussed. Let Pn denote the statement that we have to prove for all positive integer. We first check if P1 is true. If so, then we suppose Pk is true for all k greater than or equal to 1 and establish Pk plus 1 is also true. Thus Pn is true for all n greater than or equal to 1. This is an important point. Remember to check every step mentioned above carefully. Otherwise, one is likely to draw false conclusion. For example, consider the following. Here below, I am going to share a problem that tells us why second principle of finite induction is important than the first principle of finite induction. This is my given statement in which I have to prove or I have to check this formula. The sum of first and natural number is given by this formula 1 by n 2n plus 1 whole square. That actually you know the actual formula of first and positive sum of first and positive natural number is this n into n plus 1 over 2. But you will see here this formula also work, but not for all positive integer. So let us see here. Suppose Pk is true. I am not starting from here from n is equal to 1. I am starting here from n is equal to k. Suppose Pk is true. Mean to say the statement is true for n is equal to k. It means the sum of first k natural number is given by this 1 by 8 2k plus 1 whole square. That is given by only just replacing here n is equal to k and n is equal to k both sides. Say this is our question number 2. Next we check statement for n is equal to k plus 1. I am using the method here. You can also proceed as by adding k plus 1 on both sides of 2. But I am solving like this. By replacing n is equal to k in 1 on both sides, or I can say by taking the k plus 1th terms, we have 1 2 3 k plus 1 is equal to, when we put here n is equal to k plus 1, this will become 2k plus 3 whole square over 8. Now I will take left hand side and use 2 to establish the right hand side. So this is my left hand side, 1 2 3 k plus 1. In the first k natural number, I am substituting its sum, that is equal to 1 by 8 2k plus 1 whole square. So by putting here 1 by 8 2k plus 1 whole square in the replacement of these k natural numbers, the next natural number is k plus 1. Now by taking LCM and after some calculation, we can get 2k plus 3 whole square over 8. That is same as the right hand side. This shows that pk plus 1 is true when your pk is true. Now I ask a question. Can we say Pn is true for all positive integer? No, because if we check statement for n is equal to 1, then we see here statement is not true for n is equal to 1 here. If we put n is equal to 1 here in the left hand side, we have 1. If you put n is equal to 1 in the right hand side, we have 1 by 8 into 2 into 1 plus 1 whole square. This is equal to 9 by 8 and this is equal to 1. Both are not equal. This shows that statement is not true for n is equal to 1. This shows that to prove a statement we need to follow each step mentioned in finite induction. Further, here we can also observe that why does second principle of finite induction need the preceding integers. There are many problems in which pk plus 1 is true whenever pk is true. So on the behalf of only these statements, we cannot draw the conclusion the statement is true for all positive integers. That's why it is necessary that we firstly check is statement for n is equal to 1 true, then statement is true for n is equal to 2, for n is equal to 3. That's why second principle of finite induction need the preceding integers. Although in practical we do not substitute or we do not check the statement for all these integers, we only check the statement for n is equal to 1, then for n is equal to k we suppose, and we establish the statement for n is equal to k plus 1. But this is the part of your definition. The second principle of induction need the preceding integers. So I hope now you have clear understandings about second principle of finite inductions. In the next lecture we will discuss properly the exercise problems given in David M. Burton book. So if you find this lecture is helpful for you, kindly like and share. See you in the next lecture. Take care. Allah Hafiz.